Thank you to the moderators and good afternoon, everyone. My name is Salvatore Pullano. I'm an engineer, so I will try to provide useful insight, technological insight on the effect of high-intensity, low-frequency magnetic field on molecules of pharmacological interest. And in particular, I will provide technological first approach on technological standardization of a procedure to establish a fingerprint of a molecule, by molecule in this case, to provide evidence if the magnetic field can modify in sense molecular profiling, in the sense of molecular structure, the molecules, and thus if the effect of magnetic field on the molecule is additive, enhancing effect, or negative side effect. We will have a brief discussion about the magnetic field we used during the experiments, and then we used a spectroscopic approach to analyze the samples, the biomolecules. In this case, we used the FTR, Fourier transform infrared spectroscopy, and then we presented the first case study on two molecules, ketoprofen, widely known, and key oil, which was provided by pharmacological group, which is a nutraceutical product. Magnetic field is inherently dipolar field. It exerts forces on substances and charges. But during the last 100 years, physicians, medical doctors, engineers use the magnetic field. But what are the parameters involved in the interaction between the body, the tissue, the drugs, and the magnetic field? In this case, we can talk about its frequency. So if the magnetic field is a static magnetic field or time-varying magnetic field. And in the last case, we can divide the magnetic field into subcategories based on its frequency. So we need to know what kind of frequency of magnetic field we are using to understand what is its effect on the tissue, on the body, on the bone. Homogeneity of magnetic field, so the spatial distribution of the field. And last but not least, the intensity. Intensity can be in very roughly classified between weak, moderate, or high. But depending on the intensity, many physiological and biological processes can be enhanced or disrupted. Magnetic field can have two effects. One, if it is intended to be used as treatment. One, if it is intended to be used as a drug delivery system. The first case, many of you probably use this kind of approach. But in the last years, what lacks was the understanding of what was the physiological or interactive process between the field and the tissue. So what's happening inside? So in the years, we understood that on the cell, for example, magnetic field can have a positive effect or can have a disruptive effect based on the intensity. Some, for example, processes like osteogenesis can be improved by using a magnetic field. But if the field is, the intensity is too high, it can be disruptive. So we don't have osteogenesis, but the contrary. Another effect is the force that magnetic field exerts on molecules. In this case, biomolecules, the tissue, biomolecules based on water are characterized by diamagnetic effect. What is this? This is a secondary effect which is originated by an external magnetic field. So the biomolecules become magnetized because is inherently non-polar, but it became magnetic. In this case, we can use an external magnetic field to push drugs inside the body, for example. So this is why many attempts were done to use magnetophoresis, to use magnetic field to move specifically in a particular part focused on the body, drug molecules with a specific concentration in this case. The aim of this work is what is this effect on the molecule. So the molecule is modified when a magnetic field is applied or not. This is an interesting topic because it can have enhancing effect, as previously said, or it can be the effect can be net effect can be annulled. The way in which we have performed this analysis was spectroscopy, in particular Fourier transform infrared spectroscopy. By this kind of spectroscopy, we performed analysis of a moleculars in its steady state and excited states. If a molecule is excited with infrared radiation, it vibrates. The vibration can cause peak in absorbance of the tissue, or in this case of the molecule. Specifically, the high of the peak is related to the probability of having this kind of enhancement. The frequency, the position of the peak depends on the specific molecular bonds, and the sharpness of the peak depends on the interaction between the various components of a molecule. So what is the result of spectroscopy? Is a fingerprint of a molecule. In this case, we have, for example, a fingerprint of saliva, which is composed by a big absorption peak on the left-hand side, which is caused by the wet components, water. And on the right-hand side, there is the fingerprint of saliva, lipids, carbohydrates, nucleic acids, and so on. In particular, we used the ATR spectroscopy, which is a particular spectroscopy in which the sample does not interact with the molecule. So it is not crossed by radiation, but is just in brief touch with it, providing molecular profiling without a direct interaction. For this preliminary analysis, we used one of the equipment provided by Pariso, which is CTU Mega 20. And we used two kinds of molecules, as previously said, ketoprofen and key oil. The first is widely used, but if I don't well understand, the problem is that the side effects are at gastrointestinal level or kidneys. So its long-term use is not very, how can I say, suggested. Key oil is a nutraceutical product developed at University Magna Grecia and is realized by different components. So each molecule was exposed to magnetic field for 25 minutes according to a standard procedure. Then the analysis was performed within 5 minutes to avoid the relaxation of the molecule. We used the standard, very simple signal processing, and then we used some machine learning techniques in order to provide useful results that can be easily understood by a wide plethora of different specialties. First of all, as previously said by the previous speaker, standardization is very important. What is standardization in this case? Is to find the right procedure to analyze the sample, the molecule. In red is reported the standard molecule not exposed to magnetic field, and in black, the same version but dried with the low water components or other excipients component, wet components. As you can see here in the fingerprint region, many absorption peak, many information came up. So it's better to use dried version of the sample. But this version should be careful obtained because of the denaturation of many components. Same analysis was performed on key oil, but key oil, if I well understood, is not does not contain too much water, and so the shadowing effect of the water is reduced. So in case of key oil, we can use both the liquid state and solid state. These are the fingerprint of the two molecules. The fingerprints are composed by peak. On the left-hand side, there are two black peaks, which are the first constitutive peak of ketoprofen, which are the CO stretching. In this case, they are very, very low because in the formulation there is L-lysine salt, and this reduces the transition to excited state. But as you can see, the red one is the wet, the black one is the dried formulation, and the blue one is the dried formulation exposed to magnetic field. As you can see, it seems to is different, but it's very tricky to look at specific frequency, to look at specific intensity. In case of key oil, it seems that no significant variation occurs between the dried not exposed sample respect to a dried exposed sample. Then we used some machine learning technique. What is machine learning technique in this case? Is a technique in which the spectra we previously evidenced are reduced to one dot. So we are not allowed to look at specific resonance peak, but we look just at one dot, which is a representative of the specific molecule. Here on the left, there is ketoprofen on the whole spectrum, while on the right, there is ketoprofen on the narrow spectrum, on the fingerprint. As you can see, on the left is clear visible a clustering of the two samples, exposed, red dots, and not exposed, blue dots. So at first sight, we can see that the molecule is changed during the magnetic field exposure. While on the right-hand side, which is the fingerprint, we can see that the clustering is not really visible. So what does it mean? It means that some components of the formulations, benzoate or alcohol present in the formulation, can probably experience changes, structural change, but the active molecule, ketoprofen, does not change. In case of key oil, instead, we looked at clustering in both cases. So we can evidence that this kind of nutraceutical product is experiencing some changes, molecular changes, but being composed by different products, it should be arnica, devil's claw, and liposomes. Some of them could change, but some of them not. The question now is, yes, we are able to define what is exposed and what is not exposed, but what is the effect on a real scenario, real application, medical treatment? So we can just say that ketoprofen does not experience changes while exposed to magnetic field. So the enhancing or the non-enhancing effect on the treatment is due to another effect, probably on the local diamagnetic effect on the tissue. While in the case of key oil, it should be provided more insight about clinical data. And thus, I think after my presentation, Professor Gallelli will address the clinical part of the study. So by concluding, we standardized a procedure to analyze exposed and not exposed to magnetic field molecules. This standardization, this technique can be used to a plethora of molecules. We can apply machine learning technique to define if the product is molecularly changed or not. Obviously, we need a clinical validation on the effect of these changes. Just to thanks the majority of the people who contributed directly or indirectly to this work. Thank you for your attention.